introduction to hypothesis testing. So, to get an idea of what hypothesis testing is, let's talk about how it works a lot like our legal system. In the legal system, the accused are innocent until proven guilty. A jury examines the evidence and finds one of two verdicts, either guilty or not guilty. Notice that we never say we find somebody innocent. We either find enough evidence for guilt or we don't find quite enough evidence for guilt. And how much evidence does there need to be to convict? Well, this is different for every jury. And is every jury's decision correct? Nope, mistakes are made. A mistake can be made by sending an innocent man to prison or letting a guilty man go free. Let's put these ideas into the framework of hypothesis testing. Suppose a researcher thinks the population mean is different from what has been accepted. The belief that has been around for some time, the status quo, will be called the null hypothesis. Notice the notation H sub 0, H naught. The belief that the true mean may actually be different from this null hypothesized belief is called the alternative hypothesis. Notice the notation H sub A. In some textbooks, you'll notice this is called H sub 1. I always use letters that make a little more sense so I can remember what's what. So we'll call it H sub A. Another name for the alternative hypothesis is the research hypothesis. It's the thing you're looking for evidence of. It is the reason that you're carrying out the hypothesis test. We're going to state our null hypothesis in the following way. The null hypothesis, we'll say it's coming by putting a colon after that symbol for the null hypothesis. And it's going to be that a parameter equals some hypothesized value. So for example, mu equals some value mu naught, or p equals some value p naught. Notice that the equal sign always goes with the null hypothesis. And it's okay with me if you always put just the equal sign in the null hypothesis because it's really the direction of the alternative that matters when we're doing our test. But sometimes you'll see it as a less than or equal or a greater than or equal. As long as the equals sign goes with the null, you're good to go. The alternative hypothesis or the research hypothesis contains one of the following signs, either less than, greater than, or not equal to. So either your parameter is bigger than your hypothesized value, less than your hypothesized value, or you think it's just not equal to the hypothesized value. You're not sure which way, but you think it's not the same. So let's do some examples. A trade group predicts that back-to-school spending will average $606.40 per family this year. A different economic model is needed if the prediction is wrong. Is there evidence the average spending is different this year? State the hypotheses. So I'm going to state a null hypothesis and an alternative hypothesis. So what do we have no choice but to believe until we find evidence otherwise? What's the status quo? Well, we're going to have to believe for now that the average spending is $606.40. So mu, the average, is 606.4. And what is the alternative hypothesis? We want to find out if there's evidence that the average spending is different this year. Notice we didn't give a direction, we just think that it might be different. So that's going to be mu not equal to $606.40. All right, perfect. Let's try another one. So what if we had the same scenario, but we want to find if there's evidence the average spending is higher this year? State the hypotheses. Again, we'll write our symbols for our null and alternative hypothesis. And the null is that the average spending is means equals $606.40. And the alternative this time is that the average spending is higher, so greater than 606.4. All right, and another one. This time, same blurb, but we want to find out if the average spending is lower. Again, write your symbols for your null and alternative hypothesis. The null is that mu equals 606.4, and the alternative this time is that it's lower, so mu is less than 606.4. Let's move to a different example. An advertisement for a popular weight loss clinic suggests that participants in its new program lose, on average, at least 10 pounds. A consumer activist thinks this is false advertising and wants to investigate. So here, let's state our null and alternative hypothesis. So what's the null, the thing you have no choice but to believe until you find evidence otherwise? Well, it's the claim that's being made by the weight loss clinic that its participants lose on average at least 10 pounds. So how do we write that? That's greater than or equal to 10. So average weight loss, so mu, is bigger than or equal to 10. Notice we put the equal sign in the null. The alternative is the consumer activist thinks this is false advertising. So what's the opposite of that? They think that the average weight loss is less than 10 pounds. And so that's the hypotheses for this one. And one more, your local news station sales associate is selling commercial time at a premium, claiming more than 50% of households will tune into the show that airs then. A television research analyst doesn't believe this. So let's state our null and our alternative hypothesis. So what's the claim we have no choice but to believe? The status quo, what we have to believe until we find evidence otherwise. The null hypothesis is going to be the claim that more than 50% of households will tune into the show that airs then. And the research analyst doesn't believe this. So the research analyst, the research hypothesis is that the proportion or percent of households is less than 50%. Now notice that they claim more than 50% of households would tune into the show, but you can't just put for the null that P is greater than 50%, because remember, the rules of hypothesis testing dictate that you have to put the or equal to sign on the 50% in the null. Okay, so make sure you pay attention to that and always put the equal sign with the null. All right, very good. So now we've stated the hypothesis. Now we need to figure out how we're going to collect our evidence. So we're going to use P hat, the sample proportion, to estimate the population proportion P, and we're going to use the sample mean X bar to estimate the population mean mu. And you know the distribution of these statistics as long as we have a big enough sample size. So what we do when we do hypothesis testing is, for these, we're going to assume a normal distribution. We have our, and then we can standardize our sample mean or our sample proportion and look at the z-scores or t-scores for how extreme that statistic is if the null were really true. So, but again, we're going to use R. We're not going to really pay attention to these hand calculation formulas. We're going to do it once or twice, and then we're going to use R for the rest of the times to calculate our test statistics, just so we can get a feel for what's going on here. All right, so let's diagram finding the evidence for the three possible tests. So if the null hypothesis is that the parameter equals the hypothesized value and the alternative is greater than, how are you going to get your evidence? Well, you're going to have your z or t distribution drawn. It's the standard normal or the t, so it's centered at 0. And let's say that your test statistic is somewhere here. Well, how are you going to find the evidence? Well, we're going to look at how far this test statistic is in the tails of the distribution. We know if the null hypothesis were true, we would expect our test statistic to be close to the center of the distribution, close to 0. But the further away it is from 0, the more evidence we have against the null hypothesis being true, the more rare the result is if the null hypothesis were true. So we could look at, in this case, if we think the parameter that it's a greater than alternative hypothesis, we could look at the evidence of being that extreme or more in that direction of the alternative hypothesis. So remember, this distribution that we drew is under the assumption that the null hypothesis is true. And then we're going to get the probability of being that extreme. So this is the probability of the test statistic being that extreme or more in the direction of the alternative hypothesis. And how about for the less than alternative hypothesis? Well, this time we're going to look at the area to the left of our test statistic. And we're going to calculate that probability. So this probability, again, is the probability of a test statistic being that extreme or more in the direction of the alternative hypothesis and I should have put on that last one, assuming that the null is true. So that's what that probability is. So that distribution is drawn under the assumption the null is true, and we're going to measure the probability of the test statistic being that extreme or more in the direction of the alternative, so less than, assuming the null hypothesis is true. And for the not equal to, you could probably imagine, and I know you've learned this in your previous stats class, what we're going to do here is we're going to look in both directions. So you're going to have the positive version of your test statistic up here and the negative version of your test statistic down here. Whoops, that's supposed to be an absolute value sign. And if you think your neighbor's house on the right or left was robbed, but you're not sure which one, where would you look for the evidence? You'd have to look in both houses. So think of it the same way here. We need to look at the probability of being that extreme or more in the direction of being greater than or the direction of being less than. So once again, we're measuring the probability of the test statistic being that extreme or more in the direction of the alternative hypothesis under the assumption that the null hypothesis is true. So in the less than alternative, you're going to look at the area to the left of the test statistic. In the greater than, you're going to look at the area to the right of the test statistic. And in not equal to, you're going to look in both directions. So now we have a formal definition. And I'm not a big fan of making students memorize definitions, but there are a very few that I'll have you memorize. And this will be the first question on your test. The definition of a p-value. The p-value of a test statistic is the probability, given that the null hypothesis is true, of observing a test statistic that extreme or more in the direction of the alternative hypothesis. A small p-value means your test statistic was in the tails of that null distribution, so it indicates a rare result if the null hypothesis were true. So the p-value quantifies how extreme our test statistic would be given that the null hypothesis is true. So this is evidence against the null hypothesis. But how much evidence is needed to conclude the null hypothesis is incorrect? Well, this varies from researcher to researcher, and we'll make a pre-specified cutoff alpha before we conduct the test of hypothesis if we need to make a decision about it. This is called the significance level of the test. To make a decision then, compare your p-value to your significance level alpha. If your p is less than or equal to your pre-specified cutoff alpha, reject the null hypothesis, which means that you find for your alternative. If your p is greater than alpha, you're going to fail to reject your null hypothesis. You just did not quite find enough evidence for your alternative. A good way to remember this is, if the p is low, the null must go. So if p is less than or equal to alpha, reject your null hypothesis and find for the alternative. If the p is not low, then the null does not go. All right, so let's do an example. Say your statistical test returns a p-value of 0.01 and the level of significance is 0.05. Your decision and conclusion should be what? Well, let's compare the p-value to the alpha. The p-value is 0.01. The alpha is 0.05. How do they compare? P is less than alpha. If the p is low, the null must go. And if you reject the null, you find for your alternative. Let's do another example. If your p-value is 0.1 and your alpha is 0.05, we're going to compare them. P is 0.1, alpha is 0.5. This time your p is not low, it's greater than your alpha. So you do not reject the null hypothesis. You do not find enough evidence for the alternative. Very good. All right, and now the conclusion is going to be in terms of the alternative hypothesis. Sometimes you're expected to compare the p-value to the significance level alpha and make a decision, like significant evidence at alpha equals 0.05 to conclude the alternative hypothesis. But sometimes you're expected to state the value of the p-value and make the conclusion on what I call a sliding scale. Some loose cutoffs for how strong your words should be when you're doing it this way are a p of less than 0.001 is overwhelming evidence for the alternative. P of less than 0.01 is strong evidence. P of less than 0.05 is sufficient evidence. Less than 0.1 is marginal evidence, and greater than 0.1 is little to no evidence for the alternative hypothesis. So we're going to go through a couple hypothesis tests, and we're going to use these steps. You don't need to memorize these steps. This is just to help you as a guide for making sure you remember everything that you're supposed to think of when you're carrying out a hypothesis test. So step 1 is setting the alpha level. I'll tell you what that is, and if I don't tell you, use 0.05. Step 2 is state the hypotheses. 3 is the test statistic. 4 is the p-value. 5 is making the decision in terms of the null, and 6 is stating the conclusion in the context of the setting in terms of the alternative. So let's try one out. So we've got this data set from Body Shop Athletics X in Irmo, South Carolina, and they record personal record data for various weightlifting maneuvers for their members. So the data set that's attached to your lecture notes is Body Shop deadlift data, so feel free to download it and follow along with R. It contains the personal records for 41 members on the deadlift, a weightlifting maneuver where the bar is loaded and raised from the floor to the hips and back down again. Here's a picture of a very famous person doing a deadlift, starting to do a deadlift. All right, so carry out a hypothesis test at the 0.05 significance level to find evidence if the average deadlift is higher than 180 pounds for athletes like the ones at Body Shop Athletics X. So first, let's carry out the hypothesis test by hand, using R for the calculations and the p-value. So we're going to do this once or twice just so you can see and get a feel for what hypothesis testing is doing. Okay, so the first step is to state the alpha level or the significance level, and it's 0.05. We get that from the blurb. Step 2 is stating the hypotheses. The null hypothesis is what you have no choice but to believe until you find evidence otherwise. It's that the average weight of a deadlift personal record is 180 pounds. And the thing that we're looking for evidence for, our research hypothesis, is that the average is greater than 180 pounds. All right, so now we have to calculate our test statistic. So we're going to use the t-distribution because we have a sample and we don't assume that we know the population standard deviation. So we use x bar minus mu naught, the null hypothesized belief of the mean, over s divided by the square root of n. Notice that I calculated the mean of the deadlift column using R. I also did that for the standard deviation and the square root of the sample size. So I used the length function of the deadlift column to get the sample size and then took a square root of it. So those numbers ended up being what they are right here. No need to say those out loud. And the test statistic ends up being 2.763715. So now I need to find my p-value. Now my p-value, since my alternative is to the greater than, my p-value is going to be the area to the right of 2.763715. So how am I going to get that? Well, that's 1 minus the p function for the t-distribution, so pt. My number of interest is 2.763715, and my degrees of freedom are n minus 1. So there are 41 observations in my data set, so my degrees of freedom are 40. So the probability of being larger than 2.763715 is 1 minus pt of 2.763715, comma 40, which gives me that that area is 0.004. So we have a very tiny p-value. It's certainly less than alpha. If the p is low, the null must go, and we reject the null hypothesis. Now it's time to put our conclusion into words about the alternative hypothesis. If we reject the null, we do find evidence for the alternative hypothesis. So There is significant evidence at the alpha equals 0.05 level to conclude mean deadlift personal record for athletes like these is higher than 180 pounds. Notice that I don't state anything about the null hypothesis in my conclusion about the alternative. Or I can do it on the sliding scale kind of method, which is becoming very popular and in vogue these days. So here, I'll say there is strong evidence, p equals 0.004, to conclude mean deadlift personal record for athletes like these is higher than 180 pounds. This is becoming a more preferred method because it's really nice to state the actual p-value and not just that it was less than 0.05. Your p-value could have been 0.049 for all the reader knows with that first example. But when you state the actual p-value, they can see just how extreme your data was compared to what was assumed under the null hypothesis. Again, make sure to talk about the parameter, not the sample statistic in these conclusions. All right, so now let's use the t.test function, which is what you're going to use in your homeworks and your anything else that you do in this class to carry out the hypothesis test. So we state our alpha level. We state our hypotheses, mu equals 180 against mu is greater than 180. To get our test statistic and p-value, we're going to use the t.test function. Notice that the first argument I gave it was the column of deadlift weights. The next one was telling it what my null hypothesized belief of the parameter is, mu equals 180. And then the default in here is for not equal to alternative, and since I want to do a greater than, I have to put in alternative equals greater in quotes. Once you do that, you will get output that shows you your test statistic is 2.7637. Your p-value again is 0.004. Of course, your p is still less than your alpha, and you have the same conclusion as before. All right, so that is how you use R to do a t-test. So make sure you give it the data set, tell it what your null hypothesized belief of mu is, and tell it what the alternative is if it's different than not equal, if it's greater or less. Okay, so let's do another example. As part of their sales pitch, a staffing company claims 60% of their temporary staffings lead to full-time positions. An advocacy group thinks the true percent is lower. They randomly survey 25 employers of temporary staff and find that 10 of the temporary fills lead to full-time employment. Carry out a hypothesis test at the 5% level. All right, so we have our step 1 stating our alpha, 0.05. Step 2 is stating the hypotheses. So here, we're going to assume that the staffing company's claim is true and that the proportion is 0.6. The alternative is that we think it's less than 0.6, so it's going to be p is less than 0.6. To get our test statistic and our p-value, we're going to use the prop.test function just like we did to get our confidence interval for proportions back in the last chapter when we did confidence intervals. Again, you put your number of successes in first, your sample size in second, your null hypothesized belief of the parameter, p equals 0.6. We want to tell it that our alternative hypothesis is less than, so we use the alternative equals less in quotes. And then, of course, don't forget whenever you use prop.test this semester to do the correct equals false to get rid of the continuity correction. All right, so once we do that, we get a test statistic, but instead of reporting the z-test statistic, it reports the chi-squared test statistic. It turns out that the chi-squared is the square of a standard normal random variable, so this is just the square of what the z-test statistic would have been, and it's fine with me if you just report the chi-squared test statistic. It still leads to the same p-value and conclusion. You'll see that the p-value from the output is 0.02061. Step 5 is to compare your p-value to your alpha. Our p-value, 0.02, is lower than 0.05. If the p is low, the null must go. We reject the null hypothesis. And step 6 is making your conclusion. There is significant evidence. We rejected the null hypothesis, so there is significant evidence for the alternative. There is significant evidence at the alpha equals 0.05 level to conclude the proportion of temporary staffings leading to full-time positions is lower than 0.6. So notice this is just a restatement of the alternative hypothesis. And we say we either did or did not find evidence to conclude the alternative. The other way that we can do it is the sliding scale method. And here, there's sufficient evidence, p equals 0.02, to conclude the proportion of temporary staffings leading to full-time positions is lower than 0.6. Hopefully that's a good review of hypothesis testing for you.